we'll talk about selecting and implementing a regression model. The first thing to think about is, why do regressions? Other than they're kind of fun. One big reason to do regressions is you have a need to go beyond descriptive statistics. That if you're looking at a relationship between two variables, you can look at just simple means, look at difference in means. You can do t-tests, crosstab, chi-squared. But the problem is, in the real world, you have multiple variables that together can help explain the relationship between one variable and another. So regressions help identify these relationships after controlling for a number of other factors. And the third point, building theory and forming policy and practice. I assume this is why you're in the program and why you're here today, because you want to do something that makes a difference to somebody. Whether it's of interest to school principals and law enforcement leaders, your goal is to do work that can help inform people, whether it's researchers, practitioners, or policymakers. And while most regressions, you're looking at relationships or associations, under the right circumstances, they can even help support causal inference. But typically, we're running regressions just to find out what's the relationship after controlling for other factors. So some common types of regression. The workhorse here, the most common type of regression is linear regression for continuous outcomes. If you have a binary outcome, you can either do a logistic regression or a probit regression. And if you have categorical outcomes, which we'll talk about more in a few minutes, ordinal or multinomial can both be good options. So first thing, linear regression. This is where you have that continuous variable. So thinking about student standardized test scores, GPAs. You can think about the percent of students who graduate or enroll. It's not the right measure for an individual student's enrollment necessarily, but it's definitely the right measure for rates across a population where it's not just 0-1. Or something like student debt, where you can actually have some really large numbers for outcomes. Linear regression tends to work best when you have variables that are normally distributed. They follow something similar to a bell curve. And if you have a variable that has more of a skewed distribution, where you have what's called a long right tail, where thinking about student debt as an example, most people have a very small amount of student debt, but there are people who have 100,000. And if you log that distribution, it creates a more normal distribution, and then linear regression is more appropriate. Also, depending on the distribution of the data, linear regression may also work well for having those binary yes-no outcomes. And what you may do then is you may run it both ways, with both a linear regression and with one of the nonlinear models. And for those of you excited to get in and do this, the stated commands are reg and xtreg, depending on how you're doing this. And we'll go through an example of how to do this in a little bit. If you have binary outcomes, such as a student graduating, a student enrolling, a student having some amount of debt, yes or no, then you can look at either a logit or a probit model. So logit is short for logistic regression. It is not logistical regression, it is logistic regression. I know I see a lot of papers and dissertations where they say logistical. That's not the name. And whether you do the logistic or the probit model, it's what does the distribution look like? The probit model assumes tighter errors or a tighter distribution of the data, while the logistic model assumes a more widely dispersed. Now, the challenge with doing either logit or probit, and the logistic logit model is the one that's more commonly run, interpreting a logistic regression coefficient doesn't make a lot of sense on its own. So what you have to do is you have to convert it to odds ratios. When you're running the regression, you can specify to report it as odds ratios, or you can exponentiate it yourself. So either way there is fine, but just giving us the coefficient without transforming it doesn't make a lot of sense. And when you get an odds ratio, it's centered around 1. And you interpret it as the percent difference from 1. So if you get a logit coefficient that's, say, 1.2, you interpret that as whatever you're doing has a 20% increased odds of happening relative to the comparison. Or if it's 0.7, then you subtract 1, so it's 30% less. So that's how you think about interpreting these odds ratios. While if you're doing probit with marginal effects, then you can just interpret that just like a standard regression coefficient for linear regression. Some special cases to think about. So the standard logit or probit works for a binary outcome, but if you have multiple choices and there's a clear prioritization, these ordinal or ordered models may be useful. Why not just do linear regression? Because you may not know the distance between the responses. You know the distance between a GPA of 3 and a GPA of 4 is 1 point, and the distance between 2 and 3 is the same as 3 and 4. But if you're thinking about high school math course taking, is the distance between Algebra 2 and Geometry the same as between, say, Geometry and Trig? You can make an argument that's not the case, but there's a clear hierarchy. In this case, the ordinal or ordered model works well. And some concerns in thinking about these logit probit models in general, and as you have more choices, these concerns can grow. One is, do you have what are called small cell sizes? Do you just not have that much variation in a variable? Or do you have, say, for the number of students taking trig in high school, it's a fairly small group? That's a concern because if everyone who takes trigonometry in high school graduates, for example, you get what's called perfect prediction. And when a software package sees perfect prediction, it drops those cases from the model. And it's something you need to watch out for. And when you're writing up your methods, you'll note that the students taking trig were dropped because that perfectly predicted the outcome. Or you may want to combine that with some other category to retain those observations. And then we get to multinomial, not multinominal, multinomial, logit and probit. This is where, again, you have multiple categories, but the outcomes aren't in a clear hierarchy. They aren't in a clear order. So some examples, race, ethnicity. If you're interested in looking at outcomes across different groups, there's no clear hierarchy there. College majors, favorite foods. People would come up with different hierarchies if you push them. So what you do is you don't actually do a hierarchy. You're essentially running separate models where you're comparing each category to whichever reference group that you want to specify. So if you want to compare everyone's favorite foods to a reference group of pizza, you would specify the reference group as pizza, and you go from there. So those are the most common types of regressions. Some other things to think about in doing regressions. There are two main types of regressions that you see. One is a cross-section, where you're doing a regression, a snapshot at one point in time. You have achievement test scores and student demographics for 1 year. That's a cross-section. If you have multiple observations for the same school, the same students, then you have a panel. You can track outcomes over time. Most of the work that I do lives in this panel space, where I'm looking at how are colleges adapting to policy changes. So if the state changes their funding, how do colleges change over time? And since I'm interested in that over time piece, then I use panel data, which means it's multiple cross sections, and then you have to go through the process of potentially reshaping the data so a software package can read it and you can run regressions over time. Some other considerations are, what do your missing data patterns look like? How many complete cases do you have? What's your available sample size? And again, how much variation do you have in the outcome? If you're interested in looking at whether students graduated from 8th grade, and 98% of people do, you're really focusing a lot on those 2% that didn't. And you have to think, is this something where I can really draw much in the way of inference because there may not be enough variation? Other things to think about. One is choosing your dependent/outcome variable. What's the thing that you're studying? The first question is what's of interest to you? What sorts of topics excite you enough to go down the road of doing a dissertation or doing a research study? Second, what are the gaps in the literature? Where are those gaps? And then after you identify gaps, then you can start thinking about how to fill them. But the first issue to consider is, where are the gaps? And then once there's a gap, you can figure out what outcomes are available either in existing data sets or in something that you can collect. And then depending on your outcome measure, there may be issues with measurement. So some examples of measurement issues you could think about is there top coding in a variable? One of the issues that we used to have in graduate school is the GRE scores for math. Enough students would be right at the top, you couldn't tell variation. And the SAT math used to be the same way as well, where if you're interested in high achieving students, they all kind of clump together, you don't get the variation. Other issues to think about with measurement is, do you think the outcome variable is accurate? If you ask people how much they studied last week, are they going to remember it? Are they going to be accurate? Are they going to tell you the truth? So it's always worth thinking about, if there's a variable out there, are there reasons to potentially question it? Some of those may just be limitations, and others may be reasons for you to think about reconsidering things. All right, and then independent variables or your controls in the model. So these are the things that you're trying to stick into the regression to really soak up the variation and identify the relationship between the outcome and then the variables you're really interested in controlling for this other group of things. So first thing is, what does prior research look at? And if you're interested in looking at factors affecting student test scores, one thing you could look at prior scores, you could look at school resources, you could look at family income, You could look at, say, science or math classes taken. Those are things that prior research may end up using. Other things would be to look at your theoretical framework. Is there a particular way that you're looking at the world? What things do they suggest? And this is where doing a lot of research and a lot of reading is crucial to identify the factors that people would expect to see in a model. And then you have to make a case for them. You have to make a case that the variables you're looking at are relevant for your study, and also they're available, because there are things that you would love to study, but they're just not measured in a data set. And they're things that you aren't able to collect. And again, thinking about some of the measurement issues that we talked about for the outcomes also affect variables that you control for. So some other things to think about. Some people, I think, are attracted to quantitative dissertations because they think they're easy. They think they can be done quickly. I've had a lot of time working with data sets that already exist. It takes time to get things the way you want them. The first thing, Dr. Burns did a nice session about cleaning data and doing merging. So make sure there aren't outliers in the data where people were supposed to enter numbers, they didn't enter text. And then if you're merging together data sets, figuring out how you do that right, make sure that you're merging on the right variable, you didn't get it one line off. Other things to think about, missing data. It can be the case where if you have 10 variables in your model, each one has 5% missing data. You might have 5% of observations missing each of those variables, which in that case, you're doing regression on 95% of the sample, or the data may be kind of missing at random across variables. And even with 5% missingness across 10 variables, you might be missing 40% of your sample. So think about, for the things that you can observe about your observations, do the data seem to be missing at random or not? And then think about whether imputing for missing values may be worth it. And this is something that the field is been hotly debating on for decades. In general, there's more skepticism about imputing outcomes or imputing if you have a really large share of missing data. You always want to look at your correlations among your variables, because you don't want to end up in a situation with multicollinearity where your variables in your model are so highly correlated that it essentially causes panic in the stat software and it gives you useless things back. In general, if you see correlations over about 0.6, you start to get concerned. If it gets 0.7, 0.8, you should probably be dropping variables to avoid this multicollinearity issue. And then you always want to run descriptive statistics, just mean, standard deviations, and distributions for your variables. Crosstabs may be useful. You may want to just do a simple crosstab of your control, each control variable and your outcome to get a sense of what are the bivariate relationships before you get to that potentially interesting multivariate relationship. And then while you're running regressions, first of all, it's fine and dandy to use the point and click interface. That's fine. But what the point and click does is it will spit out the syntax for you. And you can learn from that, copy that stuff down, put it in a file, because then when your dissertation committee says, did you run it this way? What happens if you do this? It's a lot easier to copy and paste the stuff back in than go back and point and click, remember exactly what you did. Replication is key. You can think about this process as you put together a cookbook. And you want to set it to where you're essentially creating instructions to bake your regression cake. You're documenting, here are the things that I use, here are the decisions that I made. You want to be clear how much salt you're using relative to sugar. So you want to be clear, here's your sample, here are the variables I'm using and why. And then for the purposes of your committee, you're documenting, here's exactly the regression code that I used. So if there are issues, you can go back and change that quickly. Do not save over your data sets. Don't do it. I mean, it can be okay to have different intermediate point data sets to where you may have your individual files you started with. Then you can have a log for how you clean the data, save the data set. Then from that version, you can merge things together, save the data set then. Then you can do your descriptives. If you made any changes, save the data set again, and then doing regressions. That way, if you have to change one thing, you don't have to go back to the start at essential, or you don't absolutely have to go back to the start. You may be able to go back one data set, or since you have all of your code logged, even if you do have to go back to everything, you might just be running 5 separate files very quickly. It'll take you a couple minutes to incorporate a change on your 5th file. And this is where version control and backing things up is really important. And you don't just want to back up stuff just on your hard drive, back it up somewhere else, external hard drive. If you're allowed to use the cloud for your data, do that, because you don't want to lose something or have a computer break while you're in the midst of this, because that's a lot more work for you. Other things to think about, robustness checks. That those of you who have been through the proposal defense process, you get asked a lot, why don't you do this? Why don't you do this? You get to the dissertation defense, you'll get asked about, why didn't you do this? Why didn't you do this? And if you have all of your regression code saved, you have everything clean and organized, it's pretty easy to respond to a lot of those questions. You might do an extra couple lines of code, change a few variable names, and all of a sudden you're able to answer the questions. And that's a big time saver by putting in a good organizational structure up front. Then you don't have to worry about as many of the issues later. And you also may not have to show the 10 different tables they ask you to run. They're very often just comfortable if you say, yeah, I tried those 10 things. Here's a paragraph summary of this. The results held when I do this thing, instead of showing us 10 more tables that are identical. Other things to think about, if you're interested in subgroup commands, if you're interested in, say, looking at schools that qualify for Title I, or you're looking at students who qualify for the Pell Grant, you can do that using the same regression code, but there'll be an option if. So you can specify you run the regression if it's this group. And then if you're interested in interaction effects of your outcome with a particular group. So if you're interested in studying a curriculum and you want to know, does the curriculum affect different racial groups differently, then you can run interaction effects. So I've got a resource on how to do that with linear regression, and it's a pretty straightforward thing to do. But typically we see subgroups more, but interaction effects are also straightforward to run if you need to. Another thing to think about is displaying your results. The thing that drives every dissertation mentor nuts, and if you're looking to publish this, driving every journal editor nuts, if you just copy over your software output. Nothing is more frustrating than seeing a really long, not formatted table where you're just dumping your data, dumping your SPS onto a Word document. Think about what's important. Try to sketch out a table. And if you do that, you can get the important things and not overwhelm people. Typically, the important things are you want to have your coefficients, your standard errors, and whether the variables are significant or not. You often don't need a lot more than that. You can want things like how many observations were there. You might want the R squared. And then you want to give readers some context about what's the stuff in the table. So clear variable names, not just if you're using, say, an NCES data set, the weird alphanumeric script they give you for that. Put it in English so people can understand it. If there are any questions that any analytic decisions you had to make, like what does statistical significance mean? That's what table notes are for. And the important thing about whenever you have a table or a figure, that people should be able to get a sense of what you did without looking at the main text. The table or the figure should give them a sense. And conversely, readers should be able to get a decent sense of what the table or figure looks like just by looking at the text. That these should be fairly standalone things. So we'll leave some time for questions, but I'll do just show a quick example of how to do this stuff in Stata. And this is a paper I need to get back to. It was a policy brief that I wrote. One journal didn't want it, so I've got to get it back revised somewhere else. This is how academic life is. I took data from the Department of Ed's IPEDS data set, the Integrated Post-Secondary Education Data System, and the College Scorecard to look at factors associated with median student and parent debt of undergraduates. And I picked my coefficients based on prior research on factors affecting student debt, as well as some theory on this. And my hook on this is the parent debt measures are newly available. No one had looked at them. And I want to see if the factors affecting parent debt differ from the factors affecting student debt. So I'm going to walk through this. So I'm going to stop presenting this. And I'm going to switch to other content. So I've got a few variables here. I've got the variables that are really of interest to me are down here. I logged the debt variables. This is student debt of graduates. This is parent plus debt. And other things I'm controlling for, I've got information about admission selectivity, the percent of students who come to a college once admitted, that's called the yield rate, percent of students who took out parent plus loans, gender, race, ethnicity, percent of students getting Pell Grants, the percent of Pell recipients who graduated. I've got per student endowment, per student revenues at the college level, how much colleges rely on student tuition, and the size of the institution. So I put together that data set, and then if I want to run this, so I have debt, so that's an outcome where I'm just running linear regression. So linear regression, dependent variable, I'm looking at the log debt of graduates. Independent variable, let's say I want to see how much is just explained by race and gender. Make sure I have everything. So I can enter that here. So in interpreting these coefficients, so this is logged. So I'm interpreting this as a percent change. Coefficient, standard error, significance. So the important thing here for these variables, gender here is not significant. For race, ethnicity, white is the reference group. Asian students, Hispanic students borrow less. Black students and students who did not report race, ethnicity borrow more than white students. What I can also do then, if I want to add more variables, I can click on this code, and then I can select variables here from the right side. So now let's toss in the percent of students who were admitted, percent of students who got Pell Grants, endowment, tuition revenue. And note here, every time I'm running a command, the command shows up here. So I can copy these commands into a separate file, and I have everything that I did. You can also log everything that you're doing. So you have that as a record as well. So if I just choose these variables here, notice the coefficient on Black increased. That controlling for more factors, Black students borrow more than white students. And basically anything you throw in a model, Black students borrow much more than white students. Now, if we take this, look at the other outcome that I had here, which is the Parent Plus loan. So instead of this variable, I will change it to this variable. So notice the coefficient here on percent Black. Instead of being, it was 0.3 or so, 0.33, now it's 0.59. So Black families borrow about 60% more in parent loans than white families, even though the gap is only 33% for student loans. So if I'm putting my policy hat on, I'm thinking we have a significant issue with differential borrowing by race ethnicity, and then I'm getting into the literature on the racial wealth gap. So that's how, just a quick way of running some of these regressions. And in SPSS, there's also a way you can see the different types of regressions to run. For Stata, you're living most of the time linear regression here, binary outcomes, usually logistics, sometimes probit. Ordinal, you're getting to the ordered logistic probit. And categorical is where you have the multinomial. So that's where most of the things that you'll end up doing end up living. So with that, I will try to stop sharing this, if it will let me.